Right, so in the previous clip, we established a molecule of methane and we started to understand that we can measure the magnetic field of a proton as it spins within an external magnetic field. And what we can do is measure via a machine the magnetic field of an individual proton within a molecule. So, as we said, for methane, we have a peak X corresponding to the type of proton X within that molecule. Okay, now methane symmetrical. So what we need to do is now look at an unsymmetrical molecule, and what we're going to do is look at ethanol. Now ethanol we're going to use continually throughout building up of the complexity of NMR, but ethanol, hopefully you can immediately see, has, well, first of all, 6 protons, so there's more complexity in that situation, but due to the fact that this molecule is now no longer symmetrical, it has different types of proton. So whereas in methane each proton was identical, we'll call them all X, each proton was identical. Within a ethanol, or within an ethanol molecule, these protons are now no longer the same. However, they can be grouped together to be, or can be grouped together with equivalent protons, as they're called. And hopefully you can see that the hydrogen attached to the oxygen is completely different from all of the other hydrogens. In a simplistic sense, it's usually the atom it is attached to defines how different a hydrogen is. So this hydrogen around this oxygen is different from all of the other protons in that molecule. You can then have a look and see that this proton here is likely to be different from this proton here. Now, they're both attached to carbons, but on a very simplistic level, this hydrogen here is attached to this carbon, and that carbon has 3 protons on it. The hydrogen here is attached to this carbon, and this carbon only has 2 hydrogens on it. This carbon is also adjacent to this oxygen, and so linking in different things such as electronegativity, this carbon is going to be slightly different from this carbon, and so that means that the protons attached to the different carbons are also likely to be different as well. So what that means is, if we were to do a similar situation and scan the magnetic field as we did in the previous example, and we scan the magnetic field, then what we're going to do is pick up 3 different peaks. Now, I'm not putting any order to these, I'm not putting any higher level complexity onto this spectrum. This is a purely simplistic spectrum to indicate the presence of 3 different types of protons. That is all I'm saying on this one. There are 3 types of hydrogen. I'm not going to assign any of the peaks to a specific proton at this stage, but this is what's called a low resolution spectrum, and low resolution spectra can be used to identify the presence of different types of hydrogen. So in the first spectrum, methane, there is 1 type of proton. So there's 1 type of proton in this one. In the second spectrum, there are 3 types of proton. That's all I want at this stage for this one. We'll make it more complicated again. A few more times we'll make it more complicated, but we'll move forward.